Hello, everyone. My name is Aaron from 10E,
Hello, my name is Patrick from 10D.
Hello, my name is Wok or Pakapo from 10D.
and us, the students of Physics Honors Period C, will be talking about the life cycle of a star in both supermassive and medium sized stars. Let's get started with. Before we move into the topic of the life cycle of a star, we must first discuss what is a star in the first place. A star is a massive luminous ball of plasma, held together by its own gravity. It is made up of mostly hydrogen and helium and generates energy through the process of nuclear fusion in its core. The energy generated by this process radiates out from the core, keeping the star hot and preventing it from collapsing in on itself due to gravity. Stars come in different sizes, temperatures, and colors, and are often classified based on their spectral type, luminosity, and temperature. Stars are a fundamental component of galaxies and play an important role in the evolution of the universe. Our own sun is a star, and it is the closest star to Earth, providing us with light and heat essential for the life on our planet.
Let's talk about the two types of stars. There are two types of stars discussed in this presentation, medium and supermassive. Medium-sized stars and supermassive stars differ in several important ways. Firstly, mass. As their name suggests, the main difference between these two types of stars is their mass. Medium-sized stars, like our Sun, have a mass of about 0.5 to 8 times of that of the Sun, while supermassive stars can have masses of over 100 times that of the Sun. Second, lifespan. Due to their larger mass, supermassive stars burn through their fuel much more quickly and have shorter lifespans than medium-sized stars. While medium-sized stars can remain on the main sequence for billions of years, supermassive stars may only last a few million years before running out of fuel and exploding as a supernova. Third, energy output. Supermassive stars produce much more energy than medium-sized stars. This is because the fusion reaction in their cores is much more energetic due to higher temperatures and pressures. This energy output can have a significant impact on the surrounding environment, such as heating up neighboring gas clouds and triggering the formation of new stars. Fourth, size. Supermassive stars are also much larger than medium-sized stars. The radius of the supermassive star can be up to 1,000 times larger than that of a medium-sized star. This increased size also means that supermassive stars have a greater gravitational pull, which can influence the orbits of nearby objects. So, in summary, while both medium and supermassive stars are made up of the same basic components, their differences in mass, lifespan, energy output, and size can have a significant impact on their behavior and the surrounding environment.
So the first stage is birth. So a star begins its life as a cloud of gas and dust called a nebula. Over time, gravity causes the nebula to contract and heat up, creating a dense core known as a protostar. As the protostar continues to contract, its temperature rises until nuclear fusion begins in its core. This marks the start of its life as a main sequence star. Then, stage 2, main sequence. During this stage, a star like our Sun fuses hydrogen atoms into helium atoms in its core, releasing a tremendous amount of energy. This energy radiates out from the core, keeping the star hot and preventing it from collapsing in on itself due to gravity. Our Sun is currently in this stage, and it has been for around 4.6 billion years. It is expected to remain in this stage for another 5 billion years. An incredible fact. Now, next we have the third stage, red giant. Once a star has used up most of the hydrogen in its core, it begins to run out of fuel. As a result, the core contracts, causing the outer layers of the star to expand and cool. This phase is also known as the red giant phase. During this phase, our sun will expand and become 100 times larger than its current size, and it will also become much cooler and redder in color. Stage 4, planetary nebula. As the red giant phase comes to an end, the outer layers of the star are ejected into space, leaving behind a small, hot core known as a white dwarf. The ejected material creates a beautiful glowing shell known as a planetary nebula. This is the fate of most medium sized stars like our Sun. Now, stage 5, white dwarf. The white dwarf is the final stage in the life cycle of a medium sized star. It is a small, extremely dense object that is no longer generating energy through nuclear fusion. Instead, it cools down over time, eventually becoming a cold, dark object known as a black dwarf. So, in conclusion, the life cycle of a medium sized sun is a complex process that spans over billions of years. From its birth as a nebula to its final stage as a white dwarf, a star goes through many stages, each with its own unique characteristics. Although our sun is the main sequence stage, it will eventually become a red giant and then a planetary nebula before ending its life as a white dwarf.
The life cycle of a supermassive star. The life cycle of these types of stars is actually quite similar to most other stars. However, there are some key and significant differences that make it, not the same or differentiated from medium-sized stars, and here are some several key ways. So, information. Supermassive stars are thought to form from the collapse of a massive cloud of gas and dust, while medium-sized stars form from smaller ones, more dispersed clouds, and the precise mechanisms behind supermassive star formation is still not completely understood. Secondly, the main sequence. Both types of stars begin their lives on the main sequence, fusing hydrogen into helium in their cores to produce energy. However, supermassive stars have a much higher rate of fusion and are much brighter and much hotter than medium sized stars, which also means that they also last less because their fusion is faster, which leads into our third point, which is the lifespan, which has already been talked about in previous points. And the post main sequence. After leaving the main sequence, medium sized stars will expand into red giants and eject their outer layers in a planetary nebula and end their lives as white dwarfs. In contrast, supermassive stars can undergo multiple phases of collapse and fusion, forming dense, highly energetic objects like neutron stars and black holes are just some key phases that these stars can go through.
The fusion process in the core of a dying star. The formation of heavier elements during nucleosynthesis involves a series of steps that gradually fuse lighter elements into heavier ones, culminating a final burst of nuclear fusion that produces the heaviest elements, and the steps are follows. First, hydrogen burning. The first stage of nucleosynthesis occurs in the core of the star, where the hydrogen atoms are fused together to form helium. This process releases a tremendous amount of energy, which keeps the star burning and generates the light and heat that we see. Second, helium burning. Once the hydrogen in the core is exhausted, the star begins to fuse helium atoms into heavier elements, like carbon, oxygen, and neon. This process is known as helium burning, and takes place at higher temperatures and pressures than hydrogen burning. Carbon and oxygen burning. As the star continues to evolve, it contracts and heats up, allowing it to fuse even heavier elements, like carbon and oxygen. This process is known as carbon and oxygen burning, and is responsible for the creation of elements up to and including iron. 4. Silicon burning. The fusion of carbon and oxygen produces a core of silicon and sulfur. The temperatures and pressures at the core are so high that they can cause fusion and silicon atoms into fusion heavier elements like nickel and iron. 5. Supernova nucleosynthesis. Once the core of the star can no longer produce energy through nuclear fusion, it begins to collapse in on itself under the force of gravity. The core becomes incredibly dense and hot, and the pressure and the temperature are high enough to allow for a final burst of nuclear fusion that produces even heavier elements like gold, platinum, and uranium. This process is known as supernova nucleosynthesis. Sixth, R process and S process nucleosynthesis. During the supernova explosion, some elements are formed through a process called the R process, which involves a rapid neutron capture. Other elements are formed through the S process, which involves a slower capture of neutrons. These processes can create additional heavier elements like lead and thorium. Seventh, dispersion into space. The intense energy and pressure generated by the supernova explosion can cause the fusion of lighter elements in the outer layers of the star, creating additional heavier elements. These elements are then scattered into the surrounding space, where they can become incorporated into new stars and planets, and ultimately contribute to the chemical composition of the universe.
Now, let us look at the difference between a black hole and a neutron star. In reality, black holes and neutron stars are both the result of the collapse of a star, but they differ in their size and degree of gravitational pull. Black holes are incredibly massive objects with a gravitational pull so strong that nothing can escape it, while neutron stars are smaller but still very dense objects with a strong gravitational pull, however, still escapable. First, black holes are formed from the collapsed core of a massive star after it has gone supernova, while neutron stars are formed from the collapsed core of a less massive star. The main difference, however, is that the two stars vary in their size and degree of gravitational pull. Now, second, a black hole is an object with a gravitational pull so strong that nothing can escape it, not even light. It is surrounded by a boundary known as the event horizon, beyond which anything that enters cannot escape. The event horizon of a black hole is essentially the point of no return. Inside the event horizon, the gravitational pull of a black hole becomes infinitely strong and the laws of physics as we know them break down. Black holes are incredibly dense and have a singularity at their core, which is a point of infinite density where the laws of physics break down completely. Now, third, in contrast, neutron stars are incredibly dense objects with a strong gravitational pull, but they are not quite as powerful as black holes. They are formed from the collapsed core of a star, which has been compressed in terms of protons and electrons, which has been turned into neutrons. Hence, the name neutron stars. They are very small, typically about 20 km in diameter, but they are incredibly dense with a mass greater than that of the Sun. Neutron stars have strong magnetic fields and can emit intense radiation.
Now, we have to find the mass of the star. Currently, you have the equation velocity of orbit equals to the square root of gravity times mass divided by the radius. So now we set mass as a question mark for now. Let's say if the gravity was 100, let's say radius was 50 meters, and the velocity of orbit was 1000 meters per second. So, okay, now we have to rearrange the equation. So first we get rid of the square root. So now you have v squared equals to gm over r. Now you move around. Now you have g times v squared over r equals to m. And now you just plug that in. So now you have 100 times 1000 squared over 50, which gives you 2 million. So now let's say this theoretical star with a gravity of 100, a radius of 50, and a velocity of orbit of 1000 has a theoretical mass of 2 million kilograms. Now, we have to find the mass of the star. Currently, you have the equation velocity of orbit equals to the square root of gravity times